hard to believe how powerful semiconductor chips are today. They are no bigger than a speckle of dust, and they are critical in everything from our daily life to global geopolitics. Modern microprocessors and computing devices are everywhere. Think about appliances in your home, everything you do for your work, wearable, the medical field, and transportation. In 2022, more than 60% of the chips worldwide were produced in Taiwan. A company called TSMC, Taiwan Semiconductor Manufacturing Corporation. They are very high-end and they have extremely high volumes. Other critical countries in the production of silicon chips are South Korea, the United States, Europe, China, and Japan. The CHIPS Act is a very important move by the US government to reduce dependency the United States have from other countries in which we may have no control about external events, war, or other things that may affect their ability to continue to provide a stable supply of chips and services to the United States needs.
Microprocessor chips are the engine that fuels the modern world. They are a piece of circuitry that began in the 1940s and 50s as macroscopic structures that had to be built by hand. And over time, engineers realized was that you didn't actually need human hands to build these circuits. You could make the components of the circuits, the resistors, the capacitors, and the transistors, on silicon wafers using light chemical reactions, and you could etch in the circuits onto a very special pure piece of silicon. And over time, those circuits became smaller and smaller and smaller, surpassing first the width of a human hair, and now they're 1,000th the width of a human hair. And a remarkable thing happened that's called Moore's Law, that shrinking of the circuitry and therefore the increasing of the number of circuit elements on a chip. Over the period of 40 to 60 years, Moore's Law really drove a huge explosion in the scale of chip manufacturing and the utility of those chips across all sorts of industries, including the phones that we use every day.
As much as electronics have advanced in our lifetime, there's still much to be done to advance electronics. And so here at the University of Michigan, we're really seeking these novel technologies and to explore the edges of what they can do to develop new capabilities for the US and for the world. The University of Michigan's Lurie Nanofabrication Facility operates a 24/7 facility in which users both from the academy and from industry can come in and use advanced nanofabrication. We provide both the equipment, the infrastructure that's needed to support this advanced technology. We have more than 400 users, everything from quantum and photonic devices to high power or high voltage electronics to biotechnology, and antennas and other technologies. And there's only about a dozen of these labs of the quality of ours across the entire country. And so ours is one that people flock to come do this type of microelectronics research that has all of the infrastructure and the 135 plus tools that we have here to complete their nanofabrication work. To make microelectronics, we use film thicknesses and feature sizes that are very small, down to a few nanometers or billionths of a meter. So a single particle coming from the dust in the environment can ruin a chip. And therefore the air in the clean room goes through many layers of filtration in order to reduce the particulate counts. Clean rooms require sophisticated infrastructure that include heavily filtered air in order to reduce particulates, very highly purified deionized water that's used in experiments. They use high voltage and high temperature equipment. All of this requires a lot of infrastructure. There are multiple floors above and below the space that users occupy that help maintain this infrastructure. Finally, all the materials that we use, whether they're solids, liquids, or gases, all need to be of very high purity because the contamination of semiconductors can lead to defects that trap electrons, ruining the electrical or optical functions of the devices. Federal funding supports more than 50% of the research that's done in the LNF. This funding is received through competitive grant proposals that are submitted to federal funding agencies, which use government experts and peer panels to evaluate those proposals. One of the key challenges right now for the US is both increasing our domestic capacity for manufacturing these chips, but also advancing the research and our skilled enterprise, our skilled employees that we have available to do this type of work. We think about the dimensions in state-of-the-art transistors as being only a few nanometers. And a nanometer is defined as a billionth of a meter. So as an analogy, we can imagine the diameter of the Earth, and 1/1,000,000th of that diameter is a half an inch. So the same ratio between half an inch and the entire Earth's diameter is 1/1,000,000th. This is the tininess of the devices that we're working on. And this is why we need a facility like the Loring Nanofabrication Facility that can handle things that are of these minute dimensions. What's interesting is in other applications like automotives, we actually need quite a lot of other types of semiconductors. All of those electronics need a different set of materials.
Today, it's estimated that about 70% of the cost of a car is computing and chips inside that car. We have an industry, the one of automotive semiconductor, that has unique demands, that is in need of a lot of innovation in terms of growth, and I think present unique opportunity for the United States to become a leader in that space. The chips you put in a car are not in a pristine environment like in a data center. They have to survive for 20 years because people don't change cars very often. They have to survive vibration. They have to survive harsh chemical environments, and they have to be reliable. And so here we have many researchers at the University of Michigan that work in the space of semiconductors and that connect with the automotive industries. With the center of automotive of the United States and having this strength in semiconductor, I think is uniquely positioned to contribute to the space and to really accelerate innovation in that subsegment.
When you think about using, say, Google Maps, you open up the app on the phone, and what it's doing is it's talking back to servers at a very rapid rate. And those data centers are designed to respond very, very rapidly. That's a remarkable piece of infrastructure that people don't really think much about, but you notice it when it's gone. The information economy, you just expect to be able to get the information you want when you want it. It's been Moore's law that has powered the ability to have all of this information available at your fingertips.
In my lifetime, I've seen a great evolution of computing power from things that were very expensive and did very little to things that are comparatively less expensive and do a lot more. And so it's amazing the amount of computing power that I now hold in my hands with my phone. And I definitely want to continue that trajectory for my children and my children's children. And to do that, we need to continue investing in domestic microelectronics and everything from the R&D capabilities, things that we do here in the Loring Nanofab, whether it's investigating new materials, figuring out how to gain new functionalities from new device structures or new integration approaches, or new circuit implementations, new architectures, down to the manufacturing in new foundries and new factories. All of this needs to be done here in the US so that we can make sure that we continue to provide new electronics to meet the challenges of our future generations.